Okay, question number 3. Peaks around mass charge 32 increase by 1. There are peaks at 32, 33, and 34. Which of the following accounts for this mass difference? So what we've got here is we have oxygen 16, oxygen 17, and oxygen 18. How do I know that? How do I know it's oxygen? I look it on the periodic table and I go, who's close to 16? Right? So we go to our data pages and we say, who's close to a mass of 16? Oh, that would be oxygen. 14's way too low, 19's way too high. So it has to be oxygen. And then what the heck is happening up at 32? Why do we have a 32? That must be an O2 molecule. And this one would be made of a 16 plus a 16. Yeah? This next one at 34 would have to be a 16, or sorry, not at 34, at 33, would be a 16 plus a 17. And then this last one would be a 16 plus an 18. Now let's just take a look at the other options here. Hydrogen bonding. What does that have to do with anything in a mass spec? I've never heard of hydrogen bonding relative to a mass spec. So that's just a throwaway answer. Fewer atoms of sulfur. They might want to trick you into thinking it's sulfur because there's some 32 and the mass of sulfur is 32. But how would you get a 16, 17, and 18 out of sulfur? You know what I mean? You'd have to have half an atom, and that's just not a reasonable sort of a thing. Contamination of the sample tested, that would be a lot of contamination. You know what I mean? It would be like, I don't know. Anyway, usually mass spec is about isotopes. Other questions from mass spec? Going once, going twice, going 3 times. Sold. Okay. In that case, we are moving on to our periodic properties and... Yes. You have a question? Yes. Yes. 23. Okay. How many types of molecules with different masses exist in a sample of chlorine gas if the sample exists entirely as diatomic molecules? So we're looking at Cl2. And according to our mass spectrum, we have chlorine 35 and we have chlorine 37. Yeah? So we could have 35 plus 35. Yeah? Which would give us 70. We would have 35 plus 37, 72. And we could have 37 plus 37 gives us 74, which means there's 3 different possible masses for the diatomic molecule. Is good? Yeah. Okay, cool. Okay, we are going to start today by you guys telling me 5 periodic properties. So what I would like you to do is I would like you to chat with your neighbor and tell your neighbor 5 periodic properties. And if you want some note paper today, we will be taking some notes. What's one periodic property? Atomic radius. What does atomic radius do as we go across a row? It decreases. What does atomic radius do as we go down a column? It increases. Now, you should be prepared to give explanations for these. And I'm going to let you know what they hate right now, as well as me, because you're not actually answering the question when you do this. If you say, for example, here's oxygen, and further to the right is fluorine. So we got oxygen, we got fluorine. Why is fluorine smaller than oxygen? And somebody says, fluorine is smaller than oxygen because as you go left to right across the periodic table, the atomic radius decreases. Why is that not an answer? Yes. It doesn't explain why. It's just telling me the trend. I'm like, well, that's great. I already told you the trend. And now you said it's because of the trend. So don't give that as an explanation. So try to explain to your, yes. It can be fairly simple, okay? So for example, atomic radius decreases because as we go across a row, what happens? The number of protons increases and the number of core electrons stays the same. Therefore, what does Zeph do? Zeph increases. What force is affected by Zeph? Coulombic attraction. Zeph increases and therefore Coulombic attraction increases because Coulombic attraction is proportional to charge, which in this case is the Zeph. Is good? So that kind of gets at everything. As we go down a column, why does the atomic radius increase? More what? More core electrons, I'm going to say more occupied shells. and every subsequent shell is, every higher energy level shell is further from the nucleus. I put down 5 because this morning I asked for 4 and then someone said Zeph. So I'm like, okay, let's throw in Zeph as well. So before we go and talk about Zeph too much, you're going to tell your neighbor what Zeph stands for. Zeph is the effective nuclear charge, yes. How do we calculate it? Yes. Number of protons minus core electrons. Okay, and what happens to Zeph as we go left to right across the periodic table? Increases. How about as we go down a column? Stays the same. I don't think we need to go into too much explanation here. Or do we? We're good? Well, okay. Number of protons increases. Number of core electrons stays the same. As we go down, the number of protons increases and the number of core electrons increases by the same amount. What's another periodic property? Sorry? Electronegativity. Please define that for your partner. Define electronegativity. The ability of an atom to do what? To pull bonding electrons towards itself. What happens to electronegativity as we go from left to right across the periodic table? Increases. As we go across a period? Down a, nah, that's what I just said. As we would down a group. That's what I meant to say. Decreases. Okay. Thank you. Why? Why does it increase as we go across a period? Tell your partner. What's the first factor? Charge. What charge are we talking about? The effective nuclear charge. Would that be a good charge to talk about? Because that's something that changes as we go left to right. Okay, so we're talking about Zeph, and it increases as we go to the right. Therefore, FC, what does that stand for? Coulombic attraction. And you know what? If I were writing this for AP, I would probably, the first time I use it, I would probably write Coulombic attraction bracket FC, and then I would use FC from then on in. Do you know what I mean? I used to do that in university example all the time because I don't like writing out whole words. You know, I don't like writing out whole words, but on an exam, I would write it out the first time, and then I would write my abbreviation, and then I would be like, just use the abbreviation after that. It saves you some time. Okay, so we have Coulombic attraction increase. Coulombic attraction is proportional to charge, which is, in this case, Zeph. Therefore, stronger pulling force on bonding electrons. Is there another reason that that force gets bigger? There's two reasons that electrical force might get bigger. One of them is charge. Yeah? Atomic radius, yeah. So the separation, is that what you were going to say too?
Oh, she totally.
Okay. Separation distance. Which in this case is the atomic radius. R. And atomic radius decreases as we go to the right. And Coulombic attraction is proportional to 1 over r squared. Therefore, oh, guess what? Stronger pulling forces on the bonding electrons. Okay, maybe I should have put that at the end, but I didn't. Why does electronegativity decrease as we go down a group? Yeah, atomic radius increases. Because there are more occupied shells. That makes those bonding electrons closer to the nucleus. And if they're closer to the positive nucleus, the Coulombic attraction is stronger. Since Fc is proportional to 1 over r squared. Yay! Yes. Yeah. Further from the nucleus. Further from. Thank you. Further from the positive nucleus, and therefore the Coulombic attraction is weaker. Oh my gosh. Thank you so much, Dorothy. Yikes. Further from. Weaker. It's a good thing you guys are here to keep me in line. Okay, we got 2 more. Periodic properties. What's the next one? We got electron affinity and we have ionization energy. I'm going to do an ionization energy first. And I would like you to define ionization energy for your partner, please. What is ionization energy? It is the energy required, yep. Yes, to remove a valence electron from what? A gaseous neutral atom. Now, if we're actually going to go with that definition, if it is a neutral atom, then that is going to be our first ionization energy. If we're removing it from a +1 ion, it's going to be our second ionization energy. If it's from a +2 ion, that is going to be our third ionization energy. And we'll get into that a little bit more later. If I just say ionization energy, it is implied that it is the first ionization energy unless otherwise specified. Okay? What would the equation look like if I was to start with some sort of atom, X, which is gaseous? What would the rest of that equation look like? What would I add here? I.E, yep. And we're going to put IE1, okay, because that's our first ionization energy. And what would we get as our product? X plus gas plus an electron. And that right there is a photoelectron, okay? Because what is the ionization energy? The ionization energy is a photon of some type, probably an X-ray. What happens to ionization energy as we go from left to right across the periodic table? It increases. Ooh, what happened to our electronegativity? It increased. Oh. And what happens to ionization energy? It increases. And what's ionization energy going to do as you go down? It's going to decrease. And what happened to electronegativity? It decreased. And you know what? The argument for them is basically the same. The only thing is you don't have the same conclusion. You don't have, therefore, it's a stronger pulling force on the bonding electrons because ionization energy has nothing to do with bonding electrons, right? It's got a stronger pulling force on the valence electron, therefore it requires more energy to remove it. So it's the same argument, right? We're saying Zeph is bigger as we go across left to right. We're saying that radius is smaller as we go from left to right. Both of those things make the Coulombic attraction get stronger. And then our only thing that we have to say differently is that therefore the force on the, not the bonding electrons, but on the valence electron is stronger and therefore it requires more energy to remove. So we could say here, Zeph increases in atomic radius, decreases. Therefore, the Coulombic attraction on the valence electron increases since Fc is proportional to charge, which is the Zeph, and Fc is proportional to 1 over r squared. Therefore, more energy is required to remove a valence electron. So nothing new. If you know how to argue one, you know how to argue the other. You just have to change what you're talking about. And that means you need to know its definition. You need to know that ionization energy is talking about removing an electron. You need to know that electronegativity is about what happens with my bonding electrons. Could you write a similar statement for what's happening as we go down a period? Or sorry, not a period, a group. Yes. Is good? Now I feel like with electron affinity, we might want to take a look at the actual notes on electron affinity first, because we've got pictures that might make it just nicer. So that will be 10.1 G, 10.1 G, which is on page, hello, go there please, thank you. It is on page 38. So a large electron affinity corresponds to a large negative number. A small electron affinity corresponds to a small negative number or a positive number. So we can take a look at these guys, and you can see as we go across here, what is the general trend up from group 3A to 7A? In general, we are getting a larger electron affinity. So as we go from left to right, the electron affinity increases. Oh my gosh, guess what? Where did it go? Oh, wrong place, sorry. So we could add to our little chart here. Okay, electron affinity increases. And now we're going to ask, what is electron affinity? Tell your partner, what is electron affinity?
So it's the opposite of ionization.
Electron affinity is the energy change when an electron is added to a gaseous neutral atom. And most of the time, usually, that's going to look like this. If we have a gaseous neutral atom, when we add an electron, what do we get? We get X minus, and usually we get the electron affinity being released. Occasionally, are there two S's in occasionally or just one S? I cannot spell occasionally. Anyway, doesn't matter. Occasionally, this means this is energetically favorable. Yeah, things want to go to a lower potential energy. They want to release energy. But every once in a while, depending on who we're talking about, we might have to add the electron affinity and put energy in order to get that electron to go in. We might have to jam it in rather than it just falling in, right, and releasing energy along the way. We might have to go, we're pushing it in and it's being repelled, so we have to jam it in. Okay, so you got two choices. Either it just falls naturally, or there's enough repulsive force that you have to shove it in. Okay. And you would still end up with X minus gas. It's just that it would be a positive value there. Now, what do you think is going to happen as we go from left to right across the periodic table? Why is it increasing? Because Zeph increases. What else? Atomic radius decreases. Okay, why are you not writing? You're just making, okay, there we go. Therefore, the Coulombic attraction increases. And therefore, that electron is going to become more stable, okay? The higher the Coulombic attraction, the more stable the electron once it's added to the atom. The more stable the final position, the more energy is released getting there. You can kind of think about this like a pen falling, okay? Right? It releases a certain amount of energy. Is that releasing more or less energy? More, right? Same thing, if it can fall closer to the nucleus, it's going to release more energy. Now, I can't demonstrate this for you, but like, let's say that we were on Jupiter. Yes? What do you guys know about gravity on Jupiter? You don't know about gravity on Jupiter? Nothing? It's way, way stronger than on Earth because Jupiter has way, way more mass. So if I drop a pen on Jupiter, is it going to fall faster or slower? It's going to fall faster. And so it will be releasing more energy as it goes, right? So if you think, okay, how do I capture that energy? Well, perhaps I could have like a little thing that spins and it gets hit and it spins as it goes down. And which one would make it spin faster? Would it spin faster if it hit it on Earth? Or would it spin faster if it hit it on Jupiter? Jupiter, because it's going faster, right? So that's how you can sort of think about the amount of energy you're going to get out. If it falls further, it's going to release more energy. If it falls faster, it's going to release more energy. And it's going to be the same thing for an electron falling into the atom. Okay? So the more stable the final position, the more energy is released getting there. And let's take a little look at that on page, whatever the heck page this was, 38? 38. So as we go from left to right, the general trend is that it gets bigger. But does anyone notice anything kind of weird? Let's just look at these ones here. There's a greater than 0 in there, yeah? We go negative 27, it gets bigger, negative 122. Oxygen is negative 141, fluorine is negative 328. Okay, those are all getting bigger, but nitrogen in the middle is unfavorable. We're shoving it in. Let's look at why we have to shove it in. Nitrogen's electron configuration, 1s2, 2s2. That was weird. 2p what? 1, 2, 3. 1, 2, 3. So when we're going to take that next electron, which I'm going to draw my next electron like red, where does it have to go? It goes into an already occupied subshell. What does an electron do to another electron in an orbital? They repel one another. So when we get to nitrogen, there is not sufficient extra Zeph and sufficient smallness to overcome that repulsive force. So we have to shove that electron in. By the time we get to oxygen, we have another step up in Zeph, yes? And we have another step down in atomic size. So when we get to oxygen, it's okay. Oxygen's like, okay, the repulsive force of being in the same shell or in the same orbital is overcome by the fact that we have a higher Zeph and a smaller radius. But for nitrogen, it's not enough. It's that first one that has to go in to you already have a half-filled P subshell, and so it has to go into that previously occupied orbital, and so there is electron-electron repulsion. Yes? Can you see anywhere else where this happens? What are you guys doing? You're never like listening. You're always chit-chatting. Like every day. Are you learning lots while you're chit-chatting, or is it irrelevant chit-chat? If it's relevant chit-chat, I am okay with it because you're not really very loud. So that's the good part. If it's irrelevant chit-chat, then get out. Go chit-chat in the hallway, okay? All right. Anyone notice anywhere else where we get this big sort of drop as we go from left to right? Beryllium. And let's take a look at what beryllium's electron configuration is. Beryllium is 1s2, and then we have 2s2. Where does beryllium's have to go? It has to go into the 2p, which is higher energy than the 2s. Okay, it is shielded from the nucleus by the 2s electrons. I should have drawn it in red. It's further from the nucleus. Less nuclear penetration, okay? And it's shielded by the 2s electrons. Can you see anywhere else where we get a big spike? Magnesium. So that's going to be the same reason as beryllium, because it's going to have the same electron configuration, just one energy level higher, right? And you can see actually for nitrogen, phosphorus follows the same pattern. Like we get an upward trend and then we go down and then we go up again, right? So anytime we're, putting something into a previously occupied orbital, that first one, that's going to cause a dip, okay? And we also have a big dip over at the noble gases. Why would the noble gases? They're already stable, but more important than that, let's do neon. One S2, 2s2, 2p6. Where does our next electron have to go? It has to go into the 3s. Which is further from the nucleus and is shielded by the 1s and 2, the 1 and 2 shells, shell number 1 and shell number 2. Does that make sense? Jonah's like, no, it does not make any sense at all. It doesn't get to go as close to the nucleus. So we have repulsion from all of these guys. All of those electrons are repelling, right? And it doesn't get to go as close to the nucleus. So you were having to shove it in there. And I'll be honest with you, electron affinity, I haven't seen a question asked about electron affinity in years. Years. I don't remember the last time I saw one. Okay, they don't seem to ask about it. They seem happy with ionization energy and electronegativity, atomic radius. They just seem to be like electron affinity, whatever. They're like, yeah, I don't know. Anyway, so I wouldn't worry about it too much. If you're like, it doesn't make sense to me, don't worry about it too much because it's not going to be on the exam. I would bet money on it. Watch it be on the exam next year. I don't know. But anyway, it's generally not on the exam. If we go to our next page, we can actually see kind of what's happening. The electron is falling from an infinite distance into the valence shell. Okay, so here's our electron, here's our incoming electron, and where is it falling to? It is falling to here. Yes? So it's falling that far. This one is falling further, right? You see the distance got a bit bigger? And then here, this one follows even further. And then all of a sudden, this is lithium, this is beryllium, and then we're at fluorine, and then neon. Uh-oh. Look, neon is a smaller distance again. Yeah, because it's having to go into shell number 3. So that's less favorable. So we have to shove it in. because it's being repelled by two energy levels. This electron is only being repelled by 2 electrons, whereas this one here is being repelled by 10 electrons. Yeah? So that would explain the big difference there. That's why we have to shove the one in with neon. But like I said, what are the chances of you being asked about this? Slim to none. Will you learn about it in university though? Probably. Will you need to know about it in university? Probably. So we might as well mention it now while we're in the neighborhood. And just in case, because it is part of the curriculum, they could ask about it. As we move across a period, Zeph increases. Oh, look, we're back to arguing Zeph. Zeph increases. The atomic radius gets smaller. The incoming electron gets closer to the nucleus, closer to a larger positive charge. Both these factors make the final potential energy of the electron lower. And therefore, the greater energy is released. Is good? Ish? Yes. Y is what? O and F. Why are O and F what? Different than N? They're going up? Oh, because when we get to O, we have extra Z. And we have a smaller radius. So N is kind of a medium Z, yes? And you have to pair that electron. When you get to O, it's like the Z, the higher Z is enough to overcome that repulsive factor. Yeah? At least that's how I argue it in my head. You're never going to have it. Okay? I'm not entirely sure my explanation is like the A1 awesome explanation, but you know, it works for what our basic understanding of things is. I'm sure there's a better explanation out there in the world, but that's what we got. Okay. So I don't really think that we need to go through electronegativity per se, do we? Because we kind of did already. Okay, you guys are all familiar with Fonch?
Yes.
Okay, if you're not familiar with Fonch, you should just know these ones. Okay, this is, if you're interested, this is on page 29, but there's nothing in here that we didn't go through in that little chart today. Okay, it just kind of goes through and stresses that you should be talking about the number of protons, the number of shielding electrons, Zeph, and if because we're talking about electronegativity, we should be talking about the bonding electrons. Yeah? So you're looking for somewhere in your explanation having a definition of electronegativity, which means that you're talking about bonding electrons and not just about any old random valence electron. Does that make sense? I don't know. I feel like I've talked about all of this already today. So are we good? Okay, good. So we probably don't need to talk too much about first ionization energy either, but we will go to page 33 just because there's a pretty little picture. And we've talked about first ionization energy. second ionization energy and third ionization energy, but we haven't actually written it down. This is on page 33. So our first ionization energy, you'll notice that this guy is neutral, and we take off an electron and it becomes positive. When we have our second ionization energy, we start with a +1. Okay, and we end up with a +2. When we get to our third ionization energy, we're starting with a +2 and going to a +3. And when we get to our fourth, we're starting with a +3 and we get to a +4. You could carry on. You could do the fifth and sixth and seventh. Okay, but you don't need to. Okay, but you get the general idea of the pattern. And we'll talk about successive ionization energies either tomorrow, if we have time, or the next day, if we don't have time, because we're going to talk PES tomorrow. So make sure you bring both books tomorrow. Okay, yellow book and whatever the heck color book this is. Green, yellow and green. Lemon lime tomorrow. Okay. Oh, this is the lemon lime test. Oh, I like that. And your homework is, let's see. Where did I put it? 10.1, E, F, and G, and bring your yellow book tomorrow. Yes. Yes. In fact, I will throw it up there right now.